Australia is a vast continent, heavily endowed with natural resources. Over the years, this abundance has provided the stimulus for our technology development as we've learned quickly and efficiently to develop and manage our assets.
The lessons that this environment has taught us, first for improvisation and then for innovation, have been adopted by many emerging industries, and the capability of one of these, the Australian space industry, has expanded rapidly. Today, Australia is internationally competitive in space. We export products, services and technology. Because of our strategic location, we have broadened our skills in remote sensing. We provide a range of satellite communication services to the South Pacific region, along with extensive ground support. And we manage 1/3 of NASA's deep space network. The national focus and the drive towards excellence in space activity is directed by the Australian Space Office.
It's a major objective of the Australian Space Office to support and assist the development of Australian companies, to help them become internationally competitive, and to help them penetrate world space markets. We are achieving this by using the resources of government to provide leadership and coordination, and we are seeking competitive advantage by encouraging collaboration between our research community and our companies. We've initiated a three-element strategy. In the first element, we seek to increase the industrial capability of our companies. In the second, we're supporting emerging companies with programs aimed at new technology and new products. And in the third, we are integrating the activities of our companies with world space activities, both supported by government and those which are truly commercial.
The Australian space industry is a partnership of the public sector and private enterprise, and nowhere is this more evident than with the success of Space Industry Development Centres, or SIDCs, jointly funded and merging the technical expertise of the research community with the commercial drive of industry.
The Centre for Signal Processing is one such a consortium, with product development recently completed on an improved modem for satellite communication, using much less bandwidth than conventional systems. This has been achieved by implementing a new combined coding and modulation scheme. Application of the system is varied, allowing the expansion of the services on existing commercial trunk routes. As well as this, the process has been adopted for data acquisition from the Hubble Space Telescope. The Centre is also developing the processor for AusSat's MobileSat service, a new capability allowing communication from vehicles based on L-band satellite communications. This is used to interface with the satellite. The Space Microwave Centre is another SIDC, a partnership that includes Australia's CSIRO, space manufacturer Mitech Limited, the University of Queensland and Griffith University. This amalgamation brings together practical experience in design, manufacture and space qualification. The Centre designs and manufactures microwave flight hardware. Mitech Limited has recently completed the Ka-band beacon transmitter and earth stations for Australia's AusSat-B satellite. The Space Centre for Navigation Technology performs research and product development in the field of global positioning, a vital science used in navigation and automatic vehicle tracking. Portable global positioning devices process signals from a number of satellites and calculate an exact position on or above the Earth's surface. Complex processing is required to receive the faint spread of these signals buried in noise, and then to perform position, velocity and acceleration calculations. Development work covers testing, error research, hardware and software engineering, as well as testing image processing for synthetic aperture radar, or SAR. At the Defence Science and Technology Organisation in South Australia, a different range of tests have been conducted on SAR. Experiments are underway supporting the European Space Agency's Earth Orbiting Satellite, ERS-1. The purpose is to help calibrate the radar. Reflectors and active radar calibrators are used to provide a test pattern on the ground in the path of the satellite. Measurements in the along-track and cross-track directions are used to provide calibration and a check for geometric accuracy.
Australian industry has developed to the point of being a sophisticated supplier to the world's space community with advanced hardware and software and complex electronic systems.
Ozspace, a designer of space instrumentation, has developed an innovative global positioning system receiver, overcoming the operational problems of high vibration and temperature, a difficulty that has plagued receivers in the past. The Ozspace receiver sustains a high tolerance to dynamics with a unique open-loop phase coherent design. In addition, it will reacquire satellite signals almost instantaneously following short-term interruption to line of sight by terrain. It is produced as a 5-channel, low-cost handheld receiver able to continuously process signals from 5 satellites concurrently to provide accuracy within a few metres. Ozspace is also manufacturing a subsystem of the Along-Track Scanning Radiometer, or ATSR, an instrument for measuring sea surface temperature, which will be flown on the European Space Agency's next remote sensing satellite, ERS-2. Australian scientists are prominent in the scientific management team for ATSR. The ATSR-2 will feature optical sensing channels, and a critical component of this system is the infrared focal plane assembly being manufactured by Ozspace. This provides the eyes of the apparatus, sensors which convert infrared light into electronic signals that can be measured. Another Australian company, British Aerospace Australia, has designed and built an advanced fast delivery processor to provide immediate delivery of processed data from the synthetic aperture radar, or SAR, of ERS-1 and ERS-2. The SAR generates its radar signals from a 100 kilometre by 4 kilometre footprint. The fast delivery processor supplies active image information in 1/10 of real time. It can process information sampled from one orbit within the duration of that orbit, with the SAR unaffected by surface conditions penetrating both cloud cover and vegetation. The fast delivery processor will mean timely delivery of processed data to assist in situations where the use of immediate information is essential, such as meteorology, shipping and coastal surveillance. Space also offers unrivaled opportunities for international collaboration, such as in the case of Radio Astron, where British Aerospace Australia is working in close cooperation with Russia in this space radio telescope. Radio Astron will couple Earth-based and orbiting receivers to simulate a huge radio telescope. Our contribution will include modules for the 1.6 gigahertz L-band receiver, equipment that will be Australian designed, manufactured and space qualified. Hawker de Havilland is a leading participant in the Australian space industry, specialising in structural, mechanical and thermal activities, producing space structural hardware for international consumers. Hawker de Havilland has a new lightweight satellite under study and is a partner in the feasibility study for the Southern Launch Service.
In some areas of space technology, we are acknowledged world leaders. One such field is hypersonic testing, where hypersonic flows are generated for experimentation with speeds up to Earth orbit velocity.
WBM Stalker, in cooperation with the University of Queensland, have developed the free-piston shock tunnel capable of testing model spacecraft under simulated flight conditions, pioneering this field of expertise. Scale hardware tests using the tunnel are assisting progress in the development of a supersonic combustion ramjet known as a scramjet, suitable for space transportation systems. A critical step to producing space-qualified systems involves carrying research and development through to the application stage. VIPAC is an Australian company of engineers and scientists whose current space work on an atmospheric pressure sensor utilises stereolithography, the modelling and creation of three-dimensional objects directly from CAD/CAM data. This apparatus uses software to direct a moving laser beam, creating sliced cross-sections of the device on the surface of a photopolymer. The result is that sophisticated designs are prototyped into a solid model as soon as their concept is complete.
Australia has progressed not only in a technological sense in space, but also with commercial support in finance and insurance. No longer totally reliant on overseas underwriters, our expertise has moved us to a position of international strength through the activities of companies such as the Government Insurance Office and the Australian Space Insurance Group.
With participation in most of the major launches of recent years, our space insurance capacity covers all emerging areas of development, including small satellites and launch vehicles, re-entry capsules, commercial payloads and debris analysis. Earth-orbiting satellites, the likes of ERS-1 and ERS-2, will provide a major contribution to global monitoring. The after-effects of natural disasters such as bushfire, drought or flooding can be managed more effectively. As well as this, a broad range of studies are carried out looking at environmental factors, such as ocean currents that affect weather patterns and our fishing industries. A major thrust in Australia's space activity is in this field of remote sensing. As a regional centre for processing data and imagery, Australia has demonstrated extensive practical application experience, exporting hardware and software, developing ground support systems, advancing data processing and analysis, as well as establishing a suitable education and training infrastructure. The acquisition and processing of data is handled by the Australian Centre for Remote Sensing. With ground stations at Alice Springs in the centre of Australia and another proposal in Tasmania covering the Southern Ocean to Antarctica, this facility receives data from a number of satellites, including the advanced radar and sensors flown on ERS-1. The Australian continent, with its size, position, climate and ocean environment, offers researchers the ability to develop skills in resource management, monitoring minerals, soils, vegetation and oceans. All of this serves to make Australian technology, with its sound, practical base, very competitive.
At Tidbinbilla, near the nation's capital, the Canberra Deep Space Communications Complex is managed on behalf of NASA by the Australian Space Office.
Comprising 1/3 of NASA's deep space network, this forms part of Australia's link with NASA in space programs. Tidbinbilla tracks spacecraft, gathers experimental data and provides two-way communication to the ground. As well as this, guidance and control instructions are verified and uplinked. The station supports major deep space projects that examine the solar system and beyond. Journeys like those of Voyager, the first visitor to many of our solar system's planets. Magellan, radar mapping Venus. Galileo, on its way to Jupiter. And Ulysses, pioneering man's first visit to the sun. The key role played by Tidbinbilla demonstrates Australian skill in participating at an international level with the cooperation and confidence of her partners. Commercial satellite communications within Australia and beyond are handled by AUSSAT and AOTC. The National Satellite System is owned and operated by AUSSAT, a subsidiary of Optus Communications. AUSSAT satellites are regularly upgraded with a range of services provided, supporting the broadcasting and telecommunications industries. AOTC transmits voice, text, data and television via Intelsat and Inmarsat. The corporation also has recognised expertise in large satellite communications projects with involvement in the design, construction and management of satellite Earth stations around the world. This has been complemented by operational support with telemetry, tracking, command and monitoring for the European Space Agency and Intelsat. As well as this, AOTC supports many other international projects, from communications satellites to major international space missions.
Australian space projects are achieving a high international profile. When NASA's Space Shuttle Discovery was launched at the beginning of 1992, part of its payload was the Australian Ultraviolet Space Telescope Endeavour, a project devised by astronomers at the Australian National University, embodying unique technology for the detection of faint star images.
Over 200 companies contributed to Endeavour, demonstrating that the Australian industry is capable of conceiving, designing and building complex space hardware. At Cape York, near the northern tip of Queensland, a proposal for launch services utilising the Russian Zenit rocket is planned to commence by 1996. The site is just 12 degrees south of the equator, facing an eastern launch corridor over the Pacific Ocean, an ideal position for access to geostationary orbit, with access also available to polar and 28-degree orbits. This project will be the world's first fully commercial launch service. Another launch proposal is gearing to meet domestic and international requirements using the existing South Australian Woomera location. This southern launch service is aimed for payloads up to 1,000 kilograms, capitalising on the site's polar orbit access.
As a nation, Australia has earned an exceptional reputation for performance and quality with a well-balanced space industry. We have a skilled research and development community supported by government, industry and major research organisations, a sound and capable manufacturing industry geared to meet the precise standards demanded of space-qualified products, and extensive application experience that spans all disciplines.
Australia is well positioned to provide a range of products and services to the global space marketplace.